In this video, we're going to get a brief introduction to chemical equilibrium. My intention is for you to watch this video before we have our first class on equilibrium. My intent in making this video was so that we could go over some of the easier introductory concepts here, and then we could spend more time during the class working problems, answering your questions, and then working problems in groups. Okay, to this point in our chemistry class, we've assumed that the reactions are basically going to completion. And that means that all of the reactants are essentially converted into products. And for many reactions, this is true. They do essentially proceed to completion. And one example of that would be the combustion of octane, right? So this is like the burning of gasoline. And in this reaction, the octane is completely converted into carbon dioxide and water. But there are many other reactions that do not proceed to completion, and only some of the reactants are converted to products. In the end, we're left with a mixture of both reactants and products present, and these reactions are said to reach dynamic equilibrium. Now, we've already talked about an example of this reaction when we talked about vapor pressure, right? If we're below the boiling point of water, and we have a sealed container with liquid water, we know that some of it is going to vaporize, but once we start forming some of the H2O gas, some of that is going to recondense, and so we're going to have this vaporization and condensation happening at the same time, and when the rates of those two reactions is equal, the amount of H2O that's in the gas phase essentially becomes a constant, and so we have both liquid water and gas phase water in equilibrium at the same time. So to kind of reiterate what we were talking about on the last slide, we know from our study of chemical kinetics that the rate of a reaction depends on the concentration of the reacting species. So initially, if we start with all reactants, the reaction will start in the forward direction and we start to form products. But as the products begin to build up, the reverse reaction starts to occur, right? And so because we know that in general, the rate of reaction speeds up as the concentration increases, as we start to form more products, the reverse reaction gets faster. And as we use up the reactants, the forward reaction gets slower. And so in general, we might see a picture kind of like this, where here we're representing the reaction rates of the forward and the reverse reactions. And so initially, the forward reaction is very fast, and essentially the reverse reaction isn't happening at all. But as time goes on and we use up the reactants, the rate of the forward reaction slows down. And as we build up products, the rate of the reverse reaction increases. And eventually, the rates of the forward and the reverse reactions become equal, and it's at this point that we say the reaction has achieved equilibrium, right? So the definition of equilibrium is that the rate of the forward reaction is equal to the rate of the reverse reaction. Another way we can look at this is we can monitor the concentrations as a function of time. And so here I've just got a generic reaction. I've got the reactions A and B and the products C and D. And so initially, we have a lot of reactants. We have no products. And over time, right, the concentrations of the reactants decreases as the concentrations of the products is increasing. And when we reach equilibrium and the rates of the forward and the reverse reactions are equal, the concentrations of the products and the reactants stop changing. So at equilibrium, the things that are equal are the rates of the forward and the reverse reactions. Right? We can see clearly in this picture the concentrations of the reactants and products aren't equal. It's just that at equilibrium, the concentrations stop changing. So it would be useful if we had a way to quantify the amounts of reactants and products that we have when a reaction reaches equilibrium. And we can do that with what's called the equilibrium constant. And so this is just the ratio of the concentrations of the products and reactants when the reaction is at equilibrium. So in order to have an equilibrium constant expression, the concentrations that we use have to be equilibrium concentrations. But it is just a ratio, so I have C and D are my products, so it's the products over the reactants, and then we raise each of the concentrations to their stoichiometric coefficients from the balanced chemical equation. So let's look at an example of writing an equilibrium constant expression. All right, so we're going to write the equilibrium constant expression for this reaction. Now, it's always good to check and make sure that our reaction is balanced. And In this case, it is. So our equilibrium constant expression for this reaction is going to be K is equal to, so it's always products over reactants. So my first product is carbon dioxide, and then its stoichiometric coefficient is a 2, so I have to square the concentration of CO2. And then my next product is water, and because its stoichiometric coefficient is 3, I need to cube the concentration of water. And then the reactants will go on the bottom. And so because this is understood to be a 1, this one's just to the first power, so I don't need to put anything in terms of the exponent. It's understood that a 1 is there if I don't write anything. And then the oxygen will be cubed. All right, now just one quick note on sort of nomenclature that I should have mentioned before. When we're talking about equilibrium, we're talking about the reaction running in both the forward and the reverse directions, right? And equilibrium is defined when the rate of the forward reaction is equal to the rate of the reverse reaction. So when we talk about reactions being in equilibrium, we don't use the familiar single-sided arrow that we've pretty much used up to this point. Instead, we like to use an arrow that looks like this, where we have sort of two, let me rewrite it down here a little bit bigger, right? We have essentially two one-sided arrows. And so these are equilibrium arrows. When we're talking about reactions in equilibrium, this is what we like to use instead of these one-sided guys. Now, Microsoft products aren't great about making it easy to draw these things, and so that's why in some of his other slides, I've had some other sort of clumsy double-sided arrows. But this is the preferred way to write the equilibrium arrows. Okay, so on this slide, we're just going to kind of talk about what these equilibrium constants mean. And generally, when we're talking about equilibrium constants, we're comparing their values to 1. So in the case of what we would call a small equilibrium constant, this would be an equilibrium constant that has a value significantly less than 1. And when that happens, when the equilibrium constant is less than 1, that means that at equilibrium, I have more reactants than products, right? Because if the concentrations of the reactants are bigger than the concentrations of the products, right, I've got a small number in the numerator, a big number in the denominator, and that's going to mean that the K is very small. So an example of a reaction that has a very small equilibrium constant is this one here. In fact, this equilibrium constant is really small. It's 10 to the minus 30. That's actually good for us, right? This means that when I have a mixture of nitrogen gas and oxygen gas, it mostly stays as the reactants, and I don't form a lot of this toxic product, right? If this was not the case, right, then nitrogen and oxygen would be reacting in our atmosphere, making this toxic NO, and life on Earth would be pretty inhospitable. On the flip side, when K is greater than 1, that means that there are more products than reactants in equilibrium, right? If I have more of the products than I do of the reactants, right, the numerator is bigger than the denominator, and so that's going to yield a K bigger than 1. So this reaction, the combustion of propane, actually has a huge equilibrium constant, meaning that this reaction essentially goes to completion. I have essentially all products and not very many reactants when this reaction reaches equilibrium. And intermediate values of K, so these are things that are, something close to 1. In that case, we have significant amounts of both reactants and products at equilibrium. One example of reaction that is true for is this one here. It has an equilibrium constant of about 5. And so we would say we have significant amounts of both reactants and products at equilibrium. Okay, I think we just have 2 more notes to make about equilibrium constants in this video. This first one is that up to now we've basically been talking about using concentrations to represent the amounts of reactants and products. It turns out we can also use pressures. And one way that we might distinguish that, if we're using concentrations to represent the equilibrium, we would call this a Kc, right? C for concentration. But we could also use pressures. We could use partial pressures to represent our amounts. And in that case, we might call it a Kp. Now, one thing that I would recommend that you sort of star in your notes when we're doing equilibrium calculations, if we're using concentrations, those concentrations must be in molarity. Alternatively, if we're using pressures, those pressures must be in atmospheres. So if they gave us the pressure in torr or something like that, we need to convert those into atmospheres before doing any kind of equilibrium calculations. Okay, finally, note about heterogeneous equilibria. This refers to reactions that involve solids or liquids. And so it turns out that pure liquids and pure solids do not appear in equilibrium constant expressions. Instead, they're given a value of 1. And kind of demonstrating that is this sort of sample reaction here. Right, I've got the reaction of calcium carbonate decomposing into calcium oxide and carbon dioxide. And we can see in this illustration, right, when I change the relative amounts of calcium carbonate and calcium oxide, it doesn't change the amount of CO2 that's present. So solids and liquids do not affect the equilibrium, and they do not appear in our equilibrium constant expressions. All right, so if I was to write the equilibrium constant expression for this reaction, these solids would not appear in the expression. Instead, they just get a value of 1. So the K for this reaction would just be the products. The only product that would appear is CO2, and its coefficient is 1. The denominator would be the reactants. The calcium carbonate would just be a 1. So really, the K for this reaction is just the concentration of CO2.